Good afternoon, everyone. We are very excited that you have decided to join us today to talk about a relatively unlikely pair, Istio and databases. My name is Tyler Schade. I am a software engineer at GEICO Insurance. I lead GEICO's hybrid cloud engineering team, which focuses on building out common infrastructure service layers across multiple cloud providers and on-prem data centers. My teams work on building Kubernetes services, providing secure zero-trust application networking for workloads, and managing traffic from the edge across the various compute providers that we support. Istio is a huge part of what we do. I'm not here to sell you anything, but if you didn't know, 15 minutes could save you 15% or... All right.
All right, my name is Michael Bolot, and I'm a senior staff software engineer, and I work on the effort that Tyler just mentioned. So with that being said, let's get into it. So before we get too far into the details of what we do today with databases at GEICO, a little bit of a history lesson. So the legacy platform for databases at GEICO was mostly SQL Server. It's mostly hosted on VMs, right? In order to get away from this, we've started a V1 platform, which is sort of a way of moving away from this. It's based on Kubernetes and some of the more open source database technologies like Postgres and Cassandra and some of those things that you're familiar with. So as far as what this specifically looks like, currently in this V1 platform, each one of the database teams owns and manages their own AKS cluster. So the Postgres team has their own AKS cluster, and the databases run within that one AKS cluster. The Cassandra team has a completely separate database cluster, and all of those databases run in there. When we talk about the clients, those clients run outside of those clusters, so either on other separate dedicated AKS clusters or other places such as VMs. The way that isolation is done in this platform is mostly through Azure resources such as Azure firewalls or NSGs, and it's mostly IP-based with different segmentation done through different network zones. So there's zones that are, say, higher security classifications, and there are zones that are lesser, and there's firewalls between those zones to prevent communication from going between those different zones without approval. This setup has a couple of limitations that make it difficult to do different things. So for example, if you want to do failover, when you do failover, the IP address of your clients are going to change. So that means that the firewalls that you're using to protect your servers also have to change. And that's kind of a difficult thing to put in your environment. The way that traffic is routed through these clusters is using Istio in Istio's ingress. And the way that this is used is kind of primitive today. It's used in either one of two ways. So one way is it's got different load balancers, and each cluster gets a load balancer. And another way is just through a TCP port on one shared load balancer. Both of these kind of have problems because if you're scaling one load balancer per cluster, you've got now a ton of load balancers for each cluster, and you're wasting a lot of resources on those load balancers. And if you're doing a port for each cluster, you're also wasting a lot of ports, and you're eventually going to run into exhaustion as you consume all of the free ports on your load balancers. So the last kind of problem here is that there's a certain cost associated with this. The database teams need to manage these clusters themselves, and the Azure resources used to control these things are, as I think we're all aware, not free, right? So there's a certain cost with maintenance, there's a certain cost with finance, and there's a certain cost of operations as teams maintain these platforms themselves. So with that being said, I'll hand it over to Tyler.
So like I said, we're working on building cross-provider abstractions. And it's funny how many times when we're talking about V1 platform, we can't explain the architecture of V1 platform without talking about Azure, right? It's AKS clusters, it's Azure load balancers, it is Azure VNets, it is very coupled to Azure. And for my friends here at Microsoft, we love Azure, we're not leaving Azure, but we have to make our data centers work too, because we're building new colo facilities with thousands of servers to be able to do some things that we can't do in the public cloud as cost efficiently. So we're not leaving Azure, but we need to be able to run a common stack across wherever we are. Because we have some workloads that only make sense in one cloud. For example, I don't know, some super special ML service, let's just say, that is not something that Azure has offered yet. We want to be able to go run the same stack for our developers across that. So there are a lot of big changes for Platform V2. We're going from many small Kubernetes clusters, like Michael said, owned by individual teams, to large, centrally managed, multi-tenant Kubernetes clusters managed by our team. Big cluster, a few big clusters versus many little clusters is sort of like a canonical cloud native debate. For us, given that we're building a large part of our V2 platform in data centers where hardware doesn't auto-scale, you only have a certain set of servers that are in your fleet, it makes sense for us to be able to use our resources as efficiently as we can and try to bin pack as much as we can onto a single node. We have to deal with actual physical constraints. So one of the goals that we have for our customers is to be able to provide that same layer and it's sort of a feeling of similarity. While we may have more capacity in one cloud provider or in one region or in one data center, we want the experience of being able to deploy into that, the experience of being able to configure or consume cloud services from that to be uniform. The other thing that's pretty interesting and I think a little bit of a deviation from the norm is in pursuit of that, use our on-prem hardware pool as efficiently as we can. Our clusters are also environment agnostic. So for us, like when I say environment, I mean in the SDLC, right? During the software development lifecycle, typically you will have workloads that are at a development stage and workloads that are at a staging stage and maybe some that are at a load testing stage and some that are at a production stage. For us, the clusters themselves are production. If a customer workload is running on it, it is production. There is not an efficient way to draw a line down half a data center and say, these racks are for non-prod, these racks are for prod. It kind of causes problems for everyone, everywhere. So that is sort of the key characteristics of Platform V2 to understand. I think also worth calling out is that one of the things we've done with Platform V2 is we have completely flattened our network. All of the Kubernetes clusters, all of the pod IPs are routable on the network fabric, on the layer 3 fabric. We do a bunch of really interesting fun stuff that's been fun to dive into with BGP and setting up site-to-site peering between different cloud providers and different cloud regions, all of which is going to be out of scope for today. But any of our pods can talk to any of our other pods via IP address without any appliance or packet filtering device on path once they leave the node that that pod is running on and arrive at the node that the other pod is running on. We have no NAT. So that is a brief summary of Platform V2. Why did we make these decisions? Number one, if you've ever tried to run a database cluster with NAT, NAT is bad for databases and fundamentally impossible for some databases. Postgres and Cassandra handle this a little bit differently. Cassandra uses a peering topology, as sort of a ring topology, where every member in the peer needs to be able to connect to a seed and then begin to discover other members through gossip. That's how the cluster membership is disseminated. Those instances they advertise their IP address as the address to come and reach them on. And so if you have a Kubernetes cluster overlay network in cluster A and another Kubernetes cluster overlay network in cluster B, NAT makes this pretty much impossible. And there's some fun, tricky hacks that you can do, but at the end of the day, databases run best when they can talk to each other directly. So we have no NAT across the board. The other thing that is really powerful for us in V2 is, as I mentioned previously, our segmentation approach was zonal. It was based on policy enforcement, sort of centrally applied on path, which once you leave one cloud and go to, say, cloud number 2, and then data center, and then maybe data center number 2, by the time you get to data center number 20, unless you've been really good at managing all of your network topologies and making sure that they are identically managed and identically controlled everywhere, which is fundamentally impossible to do in the data center the same way you do in the public cloud. There's a lot of complexity that goes into network architecture that we wanted to try to simplify as much as we can. So Service Mesh solves a number of these problems for us. we get a consistent way to control traffic and to control connections. Databases, while they're not natively supported by Istio, for sure, other than some of the ones we don't run, unfortunately, they're just TCP, right? And TCP can be tunneled over MTLS in the mesh. That's really helpful for us, and we've been able to use that to provide zero trust connectivity between both clients and servers and also cluster members themselves for replication. We have been able to use that to also change the way that clients connect to databases, because currently with the V1 platform, the NAT, the regional active-passive approach that a lot of those workloads run in, to what Michael B. said earlier, that is a really, really challenging failover scenario to run through. It means a lot of the firewall policies have to change. Mesh solves all these problems for us if we could only just figure out how to run databases in the mesh. And that is what we're going to talk about next.
Yeah, so as far as the service mesh architecture goes, so the first thing is that we're running Istio with the sidecar data plane mode. The reason we do this is Ambient doesn't have quite the full feature set that we'd be looking for yet, namely with regards to things like VM support in the future. We also run multiple different Istio-D installations per cluster. We do this to provide a little bit of environment separation. So things that are managed by one Istio-D installation don't necessarily have discoverability or routability to things managed by another different Istio-D installation in the case and with the implementation we're using. We can also run multiple different Istio-D revisions within the same environment or segregated network. And the reason that we do this is when we're going to upgrade our Istio versions, because we're in sidecar mode, as I'm sure many of you know, this means that we would need to restart the pods, right? The thing about databases is you can't just go around restarting them willy-nilly. You can cause data loss, you can cause outages, so you have to do that on a more staged approach. So we'll run a current version and then the next version and allow for some failover to happen over time. One of the more interesting characteristics about this system is that users don't directly create Istio resources. Instead, what we have is a simplified API that goes and creates the Istio resources within the various clusters on their behalf. And we do this to allow users to kind of view Istio more as an implementation detail, right? They're interacting with our APIs and we're kind of representing that to them. It gives them a simpler interface and it avoids them having to understand Istio themselves, right? And some examples of what the simplified API look like are here on this slide, and they include applications. You can think of applications like a service definition. It defines an identity on the network. It can give it a host name, a selection of ports that it accepts traffic on. Then you've got network security rules. Network security rules allow applications to send traffic to another application on a given port. And then lastly, you've got external applications, which are just applications that live outside the mesh, say something like GitHub or Docker Hub, right? That mesh resources might want to access, but we can't provide different things like authorization policies on the side of the external application to enforce. And to give a deeper look at what this actually looks like, we've got this design diagram here.
All right, so this is the fun part. This is a simplified version of the architecture that we've been talking about, and this is kind of what it looks like from both a data plane and a management plane perspective at GEICO. Each cluster runs one or more meshes configured by the centralized management API. Each mesh is a set of namespaces using the sidecar-based revision functionality. We run these as very long-lived revisions. They effectively, for the duration of the cluster, do not go away. We have multiple trust domains that we run in each cluster with centralized Spire servers, and then we have a separate Spire architecture that I'm going to kind of leave off to the side here in the interest of time. But one of the things also that's been great for us about Sidecar is the ability to actually use our Spire architecture, not just use it natively, but also be able to use multiple and control that on a mesh-by-mesh level. That is very, very helpful for us. Each mesh has its own trust domain. So each cluster, if we step outside of the mesh level, each cluster runs a cluster agent, which is responsible for doing basically everything and will be the only thing, barring a break glass emergency SRE-involved scenario, that ever configures Istio. It configures Istio. It also configures some higher level CNI things like network policies. We run Cilium as our CNI. The BGP features are very, very helpful in a data center. And then it also is responsible for performing service discovery. Service discovery is pretty integral. When the user defines an application abstraction, we receive a set of criteria to be able to go and discover instances of that service. Usually this is a composite of Kubernetes namespaces and then pod labels. We have our own mechanism for service discovery that is not natively sort of plugged into Istio. So we do service discovery out of band and then push service discovery results back into Istio. This allows us to be able to scale our multi-cluster approach without having to take a lot of the circuitous paths that you can sort of have to get to, and to be able to control traffic much more granularly than, say, leveraging Istio service discovery across multiple clusters lets you do. Service discovery takes place by this agent, but then is disseminated via gossip over Kafka. So each agent, the lifecycle of an agent is the agent is installed, and all it knows about is the address of the management server to go and authenticate. It receives in a architecture that may look very similar to something that you guys have seen before if you've used Envoy. It receives a bootstrap configuration, right? And then receives gradual Delta-based updates as things change within the system. It's kind of like that same pattern, just even further out at a cluster by cluster level. When service discovery takes place, each individual application has a unique Kafka topic that is partitioned for that application, which means that because we require for connectivity every application through network security rules to enumerate every service that it's going to accept a connection from and every service that it's going to connect to, we can cut down on the set of service change events that we actually need to follow because we partition by application. So we're able to say, for example, if I have a cluster, if I have a pod in cluster A that has 3 clients in cluster B, but no clients in cluster A, we know that cluster B needs to follow that pod service discovery changes, but we don't actually need to manage that service registry updates in that cluster, right? So it allows us to sort of balance and sort of fan out some of the work and de-scope the amount of meaningless events that we're pushing across our system. I think the last key point here is that configuration always comes into the management plane. Like I said earlier, it's persisted in a database. We use Cassandra. We like to dog food. We like to try out our own stuff. So yeah, that's what we're doing. The agent initial configure, the bootstrap config that we use is very, very small. It is very, very light. Almost everything is an initial push after the handshake over gRPC, and then Delta updates over Kafka. So that is sort of under the hood what the service mesh architecture looks like.
So there's a couple of things that we learned from trying to run databases within this architecture. So the first one is that the communication between database replicas isn't trivial. Databases will tend to communicate between replicas. A good example of this is Cassandra, which will gossip between the different nodes. So you end up needing to do weird things like having authorization policies that allow service accounts of the pod itself to communicate with other things matching the same label selector. So it's a little weird, but it's something that you can manage. Another thing is that operators within this space are another challenge that you've got to overcome. 2 issues that we found with this was first that the operators need to actually call out to the various database pods themselves, and they usually do so over unusual ports. A good example of this is Cassandra, which will manage the Cassandra pods over a management API running on port 8080. It's a little bit of an unusual thing. In addition, operators will typically run with a Kubernetes mutating webhook configuration or a validating webhook configuration. And when they do that, the Kubernetes API server is going to be looking for a certificate that's signed by, or that has a SAN for a very specific host name, namely the service that webhook is running under. So if the API server tries to contact the webhook and it sees the cert that the sidecar pod is presenting, it won't have that SAN and it'll throw an X509 error. So you can solve this with a pure authentication policy sent to permissive, which will allow the connection to go through and succeed. But again, it's another thing that you kind of got to think about, and you've got to build all of these different little things together to create a functioning database operator. So you have to have all those little tiers together. And this kind of brings us to the next point here, which is that all of these operators are kind of a more manual process to onboard. We have to think about how each one of them works. We've got to try out each one of them. We have to see which ports they're using, which things work under what conditions. And it's a case-by-case basis. There's no hard and fast rule of if we do these things, then database operators will run. It's you've got to try specific database operators. You've got to implement specific rules for that database operator for it to work properly. Yeah, and one of the other things to keep in mind here too is the addressability of the pod IPs themselves. So typically these operators will reach out to the pods specifically over the pod IP rather than a service entry, right? So the mesh needs to be aware of how to route those pod IPs specifically and not just say through a service, right? And you've got to configure the service discovery to work appropriately alongside that. So all these kind of things have to work together to get a functioning system in this case.
So now that we've built this out, we're still running V1 in production. Where we're going next, obviously first to production. Data center builds are fun to manage, and it's the world of atoms, not bits, and you can't just do things faster when you're waiting on a shipment or waiting for physical connections to land. So we are actively testing and working on driving customer adoption, but we are not ready for production from a platform standpoint. So during the extra time that we've gotten during those delays, we really want to push the limits of our scalability. We want to figure out at what point do we knock things over. We want to be able to start doing some t-shirt sizing to ensure that we're properly resourcing the sidecar pods for the various database clusters. We know, for example, that Cassandra's replication is incredibly chatty. And so we need to be able to give more resources, for example, to a Cassandra cluster sidecar than we would if it was just a Postgres database. And this is something that we have to do because the database pods aren't usually used to the fact that they're running in a mesh. CNPG, which is how our database team runs Postgres, is not mesh aware at all. And it was a very fun, exciting journey to go make it work in the mesh. There's other things we'd like to be able to do too. We want to be able to integrate more Envoy protocol specific features for being able to do database protocol specific features, to be able to do layer 7 observability of the actual database protocol itself. That's like a long-term goal. We have bugs to fix. And then the kind of funny picture over to the side that you'll see, one of the things that we've talked about a lot through designing this is, from an API design perspective, are we taking sort of a cathedral, monolithic, encapsulated world, or are we taking a bazaar where users can come in and buy this and buy that, right, and sort of self-assemble? During the process of actually watching users onboard, not only were we confirmed in our suspicion that actually asking users to write their own Istio configs was a bad idea. It turned out that the high-level APIs that we put together to encapsulate Istio configs was also a bad idea, because we need a yet higher level API to be able to allow sort of a blueprint approach where somebody designates that an application is a Cassandra cluster, and then all the Cassandra-related config just happens from there for them, instead of what we do right now, which is you define an application, you define its network characteristics, and then you go set up the requisite network security rules to be able to allow connectivity from place to place. Based off of early user feedback, it's one level up still. I'm not sure how high we're going to climb the tower of abstraction, but right now we still have room to go. All right, so what would have made this ultimately easier for us? Well, the first thing is it would be really nice if Istio and really Envoy, because that's where the gap is, supported database protocols, more database protocols natively. It's awesome that we have MySQL support. It's awesome that we have Redis support. We are going to adopt the Redis protocol specific features for Valkey, but the Postgres filter is in contrib, which means it's not in Istio, and it is not quite fully baked. We would love if we could sort of natively decode and observe that protocol. That's obviously going to take some time, but we'd like to see that happen. It would have made this process much easier. Also, like wishlist, if an Envoy filter, like if there was a native Envoy filter in the upstream builds to be able to decode Cassandra protocol at all. At least for Postgres, we have something a little bit more than that. But like being able to decode the CQL wire protocol would also be really, really cool. One of the advantages that we do have with Cassandra is that it natively supports SPIFFE for client authentication and authorization, which we don't have with Postgres. So we're able to sort of handle the fact that we can do some more advanced things for mesh client authorization in Cassandra that we just can't do at all with Postgres. So Postgres would have probably been more helpful in Cassandra, but ideally long-term, both would be great. And then, yeah, the other thing, why didn't we run ambient? Because ambient is so exciting right now. There are some features that we think to be able to run in the constraints that we have that we'd like to see ambient support before we really get there. Being able to use Spire, being able to use revisions, being able to run multiple instances of an ambient mesh within a single cluster would be really, really helpful and would save me a ton of cores as somebody who's doing capacity planning right now. So big fans of ambient long-term. Also, if we could get VM clients for ambient, we do have many older workloads that run outside of our sort of modernized platform on legacy VMs. Being able to onboard those as mesh clients via Envoy and running Istio sidecar on the VM is really, really helpful, but there's, again, not similar support for ambient yet. So those are some things that would have made this easier, and then I'll give the rest of it to Michael to close us out.
So we've talked a lot about the various things that we want to do here and that we've done in the past. And if this type of problem seemed interesting to you, namely a cross-platform, cross-provider service mesh based on Istio, please come up and talk to us because we are hiring and we would love to talk with you more. And lastly, thank you for coming to this presentation. We've got a QR code here if you want to leave feedback. And since you guys know that we're not just a bunch of liars, we also have a GitHub repo where we demonstrate some of these Istio concepts that we talked about how to actually run these operators. So you can go check that out and see the manifests yourself. With that being said, any questions? Thank you, everybody.
Yeah, I'm from the Microsoft AKS. I have like one couple questions.
We'll be around all week. We can do all the deep dives. Like I said, we're not leaving Azure. I promise we're not leaving Azure.
You mentioned some support of Cassandra and Postgres. I think Envoy is a very flexible software, and I think can just build on. Actually, I just have a talk about people. I built on this, so I think you can build it out.
Yep.
Yeah, and I have a question about. I remember you mentioned you are. Sorry, thank you. You are trying to use plan network, so all your pods can talk to another one. So, do you ever facing that IP exhaustion issue or?
No.
So do you like allocate big enough CIDR? Okay.
Yeah, and an interesting networking tip is that there are some prefixes that are designated that you may never have to route to, and 10.8 can grow. So yeah, we have plenty of IPs. Eventually, we would like to just switch everything over to IPv6, but that's,
Cool.
Yeah.
Cool. Good to know. My last thing is not literally a question. You just mentioned Istio ambient mode don't support a revision. I think it actually supports revision because we AKS are building a managed ambient product. Basically, yeah, we try to explore it a bit. Yeah, there are some ways to still use revisions under the ambient mode. Yeah, if we have chance, we can.
I think control plane revisions are supported, right? But actually getting Z-tunnel revisioned is more challenging.
Yes, it's still, yeah, but we can talk more about that. Cool. Thank you.
Hi, I noticed that in one of your slides you mentioned that you actually have two mesh within one single cluster, but you actually have two cluster. I'm wondering why you have this design like within one cluster have like product and dev mesh, and actually cross multiple cluster you have that instead of you have like one cluster for only dev mesh and another cluster only for the product mesh.
Yeah, this comes back to what I had mentioned about the constraints of running in a data center with a limited pool of hardware that doesn't grow, right? Like it grows, but it grows on a multi-month purchase cycle as opposed to just being able to auto scale like you can in the cloud. You can kind of imagine each of those clusters. There are more clusters if I were to diagram our entire system architecture for you. We support N clusters and we support N meshes. A cluster is a regional boundary. It is a provider, it is a compute provider within a specific region across one or more availability zones, right? That is how we define a cluster in the mesh. Right now, that corresponds to a single Kubernetes cluster because, again, of hardware limitations on-prem and designing our system in the cloud around on-prem so that it models on-prem. But over time, the concept of what a cluster means can become multiple in a region. The system is architected to support multiple in a region. But at the end of the day, like I said, if we run it, it's production for us. Like if a customer is using it, it's production. And philosophically, there's some interesting stuff if you really think about like why you would want a dev Kubernetes cluster. It probably, in a lot of cases, comes down to discomfort with your own ability, like not you personally, but like a team is usually pursuing that because they're uncomfortable being able with their ability to manage, right? Like they want to be able to reduce, usually people say they want to reduce blast radius, right? Unfortunately, on-prem, we only have so many servers, which means we need to use them as efficiently as we can, which means that we had to get comfortable being able to upgrade in production, for example. And yeah.
Thank you.
All right. Thank you, everyone. Have a great KubeCon.